Now, the more you start to work in R, the more you find yourself repeating the same procedure, often several times. For example, let's suppose you're plotting one scatter plot after another, and you want to include a regression line on each plot. You want to somehow customize what you're doing. Well, there is a way to customize those procedures in R without having to just repeat code over and over and over again. And we call those custom functions. Now, one of the coolest things you can do is write your own function. These custom functions, they let you define a specific action that you want to take on your data, and it lets you easily apply that action to new data. Now, this can be anything from maybe you're calculating a statistic, or you want to create some customized plot that's got funky colors on it. You can even combine several outputs into a single display. If we want to make a custom function, we first have to define one or more inputs, followed by some action that we're going to do on them, and then an output. And so your function is going to take the input, perform an action, and then spit out some output. That might look like a transformed data set or some kind of plot. Now, R has built-in functions like summary or median. We've used these throughout the course. But here's a pitfall that my students and I even fall into sometimes. And it's this: overwriting a built-in R function. In fact, some of R's built-in functions are just common words like contour or mean and median or plot and summary. And so as we start creating our own functions, we think, oh yeah, I want to define a plot. Let me call it plot. Well then, to R, I've just redefined what plot means. Here's an example. Let's suppose we overwrite the built-in function plot. In my code, I say, hey, I want plot to be the histogram of X. So now when I try to run plot on my data X, I get an error. To account for that, I actually have to remove it from the R environment. And you do that with the command rm, which stands for remove, of plot. So here's what I recommend. Before you create any new function, always type a question mark and then that new function name to see if it's already in R as a function. So as long as you keep that in mind, your work to create custom R code will be well on its way. Now, these custom functions that we create, they can be quick and dirty one-liners, or it can be a body of code that's long and elaborate. In fact, I remember my PhD thesis had pages and pages and pages of R code. And when I first started writing code in R, I didn't know how to create custom functions. So every time I looked at a new data set, I would type all new code to analyze it. And if I wanted to, say, drop the bin size of one of my histograms, I would go through and search all the pages of my code, and I'd find where I used the histogram function, and then I'd change the bin size. I remember one day I asked my office mate to look over an error in my code that I was getting. And so she comes over to my computer, and then all of a sudden, her facial expression looks disgusted. And I'm like, oh my gosh, what's wrong? Are you okay? And she said, your R code, it's awful. Why do you keep repeating these lines over and over? And why are your variable names confusing? Well, as you can see, she didn't hold back. But then for the next 2 hours, we sat down and began to write custom functions in R. What was 3 pages of redundant, unclear code became half a page of beauty. I mean, I had no idea that so little code could do so much analysis. So I want us to get some practice writing functions in R that automate the data analysis process. So this is going to make our R code cleaner and less repetitive. So let's get started. Now remember how functions work. They take arguments, They do something to them, and they return a result. Here's the syntax that we use for creating a function in R. So here we'll call that new function, new dot function. And we use the function command with our arguments in parentheses. Now we need this open bracket and the close bracket below to indicate that all of our code lies on the inside. And on the inside, between those two brackets, go our lines of code using arguments. For example, look here. We can create a custom function that replaces the mean function in R. Check it out. We're going to call that mean.fun, and it's assigned to a function that takes in as its input the data x. There's that open bracket. So I'm going to define my mean, or my.mean, as the sum of x divided by the length of x. That's just what the mean is. And then I'm going to return that value. So here we've created a function that takes a mean of the data set x. Now, once you've defined a function and you've given it a name, you can use that function on a new data set. Here, let's set the seed. So set.seed of 3456 just ensures reproducibility. So if you want to generate this same code that you see on the screen, you use that set.seed and you'll get the exact same output. So here, mean.fun of open parentheses 0:20 says, I'm going to take the mean of the numbers between 0 and 20. And notice that output of our function gives a value of 10. And here we've simulated a random normal sample of size 300 with a mean of 0 and a variance of 1. Notice when we apply our mean.function or mean.fun to that data, we get a mean of approximately 0.02. And while the mean function has only one input, say the vector x, we can also extend our function to define multiple inputs. For example, let's adjust the function so that it has an input called delete.outliers, which, when true, automatically deletes outliers before calculating the mean. So this is going to come in handy whenever we have to do exploratory data analysis. Check out the code you see here. Now we've augmented mean.fun as a function that takes in not only x, our data, but delete.outliers. We're going to initially set this equal to f for false. So that means we don't want to use it. But here's the code that goes with that. So we need that open bracket. Now, if my delete outliers equals false, then I'm just going to calculate the mean the regular way. So my mean is the sum of x divided by the length. But if delete.outliers equals true, then first I'm going to calculate the original mean, so that's my orig.mean, and my original standard deviation, orig.xd. And then I'm going to take the outlier log. So now I want to find all the outliers in my data set. So here's what I'm going to assign to that outlier.log variable. All the values of x that are larger than the mean plus 2 times the standard deviation. Or all values of x that are less than the mean minus 2 times the standard deviation. Right, so basically I'm sort of putting a 95% confidence interval around the data, and then I'm logging all of the points that fall outside of those. Those are my outliers. And so now I'm defining a new variable, x.noOutliers is equal to the value of x where my outlier log is equal to false. And so now my mean is going to be the sum of x without any outliers, right? I've taken those out, divided by the length of it. And I'm going to return that my mean. Now, a couple of things to note about this function. In the function, the input, we've added that equals f after delete.outliers. So that means that's going to serve as a default value. And if you include a default value for a function input, then if the user doesn't specify that value, it's okay. R is always going to use the default. Now you could even add a default data vector. So we can set x equal to, say, random norm of 10. Now, when you have a logical input, which is either true or false, such as our delete.outliers, it's common to use if statements. Those help us define the action for when the input is true, and then define what we're going to do when it's false. So if this is the case, do this. If this is the case, do this. So that's why we need those if statements. All right, here's an example of our function in action. Let's create a vector data set with 100 samples from a standard normal distribution with one teeny outlier at 400. So again, I've set my seed, and now I've set my data equal to random normal of size 100, mean 0, standard deviation of 1, with the value 400. And notice in the front, I've combined those with the command C. So now I want to calculate the mean of that data. So mean.fun of data, but I don't want to delete any outliers. So delete.outliers equals false. Notice here I get a mean of that data set of approximately 3.9. But look what happens when I set delete outliers equal to true. Now that value of 400 gets removed from the data set. We get a mean of minus 0.02 approximately. So our code is actually working. Now, one common task is to modify an already existing function by just changing one or two of the parameters of that function. So look here. If you find that you're frequently adding certain things to plots, like reference lines for the median or the mean, then to create a custom function will allow you to make that process so much easier. Let's start by creating a custom histogram with an added reference line. And so we're going to call this hist.fun because it's a fun histogram. And in fact, the first thing that we're going to do is add the median to that histogram. We're going to add a vertical line right where the median should be. Here's the code to do that. So hist.fun is going to be a function of x. And now I'm going to define this additional term here, add.median equals true. Right? So when I make this true, I want you to put the median on the data set. We need an open bracket to start our function. So first, we just take the histogram of x. And then notice here, we use that if statement. If add.median is true, then add in line, A, B line. That means add a line from A to B. And I'm going to add a vertical line. So that's the V equals the median of x. Here, LWD equals 3 assigns the width of the line equal to 3, and the color is blue. Here's the output from that. So I want to run my hist.function just on some random exponential data. And add.median is equal to true. Notice here, you see our histogram, and we've automatically located the median of that data set and plotted it with our function. Now, we don't have to stop there. We can actually add the mean as well. So let's do that. This is going to be a vertical line also located at the mean. Here's our code. So let's highlight what we're doing differently here, which is near the bottom. If add.mean equals true, now we're going to add another AB line. Here, a vertical line at the mean of x. I'm changing the line type because I really want to differentiate between the median and the mean. So LTY equals 2 means change the line type to a dashed line. And I'm still going to give it a weight of 3. Here's the output of that code. Notice here, we've got our histogram with now our blue line, which represents the median, and the white dotted line represents the mean. So why stop there? What else do you want to add to this function? What about a legend? We could do that as well. Go back to your code. All right, here's our histogram. And notice now at the bottom, if add.legend equals true, we're going to add a legend in the top right corner. And in that legend goes the median and the mean. And I also want to put the lines that associate with those medians and means in a color blue and white. So you see how we're just building on this code that we're already writing, right? We're just adding features to our function. And notice at the top line, every time we add a feature, we have to add that as a component, as an input to our model. So now we're inputting our data X, a command for add.median, to add the mean, and now to add the legend. So we have to specify all of those. Here's the output of our function. Let's apply hist.fun to some random exponential data, 100 of them. And notice here, we're going to add the median, add the mean, and add the legend. So look how we're starting to build a body of code to give us really unique output. Don't stop there. There's so much more we could do. In fact, let's add some color to that histogram and color those lines. Check out this code. Now go to the bottom. You'll see here where we've now added a color to the histogram. In that second line, hist of X, and now we're adding the color, cadet blue. Notice that we also changed the color of our mean line from white to red. Check out how this changes our output. So hist.fun of those 100 random exponentials, but now we've got a cadet blue colored histogram. Now we could just as easily try this function on other data sets. Remember our iris data? So here's the histogram function of the petal length, adding the median and adding the mean as well, and then coloring that histogram and putting a legend on the side. Notice how much information you get from this graphic. Right? It's really clean, it's very visual, and you immediately know about the center and the median of your data. Here's our empty cars data set in miles per gallon. Now notice here, this histogram has only got 5 bins. It doesn't really look too great, but it still works on our function. But that gives me an idea. We should add a way to change the break size of our histogram. Right? We wouldn't even use that histogram that we just looked at because the bin size is too big. So let's augment our code to account for that. Here, we've now added B for breaks. And we're going to let our breaks be a sequence from the minimum value in our data set to the maximum value. And the size of the length is the number of breaks. So notice, when we call the histogram, we're going to set breaks equal to B. But one other thing to point out there, notice that we also have added a number of breaks in our histogram function. So the num.breaks equals 12. So this is going to give us a place to go to adjust the break size without having to go through our code. So check out the histogram. When we call the histogram on X, we've got the color, but now we've set our breaks equal to B, where B is our num.breaks as the length. Here we go. Here's output. We're going to run hist.fun on that empty cars data set of miles per gallon, add.legend equal to, and notice here I've changed the breaks. And do you see how that's augmented my histogram? Now we could generate plots with different breaks just so you could compare them. And we do that with the par command. Par mf row of C12. All that command does is let us put 2 plots side by side. Let's look at the histogram of our chick weights with the number of breaks equal to 5 versus a histogram of those chick weights with the number of breaks equal to 20. So check this out. Now we can visually see the difference that setting those breakpoint makes. And we've got the legend there and also the title. Now, notice here, we can do plots with different breaks. What if we wanted to add even a third plot to compare to those two? Well, we can change that par function to 1 and 3 and add even a third histogram that in this case has 30 breaks. So check this out. Here we've got our plot, and our function has now taken those data sets, plotted all 3 of them right next to each other so that we can visually compare. So imagine how easier your analysis could be if, as soon as you get a data set, you're able to generate beautiful graphics, get the output, and also change those parameters. Immediately change your bin sizes so you can begin to see the shape of your data. Let's try it again here. Here we have the empty cars data set with outliers. And there's the output that we get when we put that on our code. Now, we can add as many custom procedures and plotting parameters as we like. And in fact, we could do the same thing for scatter plots. Remember, we use scatter plots in almost every lecture of this course. We're always trying to get the scatter plot or the range of our data. So let's add a mean to our scatter plot function. Here's a new function that we're going to call scatter.fun. And it's going to take in x with a default value. Notice now, I'm specifying that x is a random normal of size 1000. And y is also going to be a random normal of size 1000. So this scatter.fun has data in it that if you don't specify any data, it'll automatically use these values. And here, if I add the mean equal to true, then that's going to plot the mean of my data. I want to plot x versus y with a point character, or PCH, equal to 20. Now, if my add.mean is equal to true, I'm going to add a horizontal line at the mean of y, and I'm going to add a vertical line at the mean of x. So that's our code. Let's run it just on the default. So here we just did scatter.fun, open and close parentheses. So what that's doing is automatically just generating 100 random normal variables. And then it's going to do the mean of x and the mean of y, which are the two lines you see here, the vertical line at 0 and the horizontal line at 0. All right, so we're going to add to this. We can create a custom scatter plot with some actions. Let's create two plots, one where there's not a significant correlation and one where there is, and see if we can plot those next to each other with our function. First, let's generate the data. All right, so we're going to set our seed so we can make sure our results are reproducible. And we're going to assign x to just a random normal of 100. And then my y that's going to be uncorrelated with x, or y.uncore, is also a random normal of 100 values. But I'm also going to create data, y.core, that is correlated with x. In fact, that data is going to be equal to the vector x plus a small amount of noise. That's that random 100 with a mean of 0 and a standard deviation of 0.3. Okay, let's check that out. What happens when we run our scatter.fun on x with uncorrelated data and x with correlated data? Notice here, our function generates these two graphical outputs. On your left, you see random data, which has no relationship. And then on the right, you see the data that we generated, x equals to y plus noise. And you see how that data falls nicely along a linear pattern. And notice, we've also got the mean of x and the mean of y on both of those data sets. Now, we could add a regression line to this. I mean, if the correlation is significant, we could make the line green. And if that correlation's not significant, we could make it red. So you never have to do another regression analysis. You just run it through this code. Here's how we do that. So for our input, we're going to use an add.regression term and set that equal to true. So the default is to always add the regression line. We've talked about the plot command and the add.mean command. And notice what we're adding to this code. If add.regression equals true, then I'm going to do a linear regression. I'm going to model a linear model of y on x. And then from this model, I'm going to pull out a p-value. So I can do an ANOVA of the model, and that $sign says, hey, take the p-value, the probability that you're greater than f, and assign that to the term p.value. If my p-value is less than or equal to 0.05, then I want my regression line color, or regline.col, equal to green. And if my p-value is greater than 0.05, I want my regression line color equal to dark red. And then AB line is going to add my regression line to the data set. All right, let's check this out. We're going to, again, call our function on the uncorrelated pairs and the correlated pairs. And here's what we get. We've still got that same scatter relationship, but notice now we've added the regression line. Red when we don't have a significant p-value, and green when we do have a significant p-value. Another thing we can add is a conclusion, right? This might tell us if the correlation coefficient is significant and what it is, its associated p-value. Here's how we do that in our custom function. If add.conclusion equals true, then we want to do a correlation test on x and y. So that's core.test of x and y. And I'm going to assign that to c.test. So I want the coefficient to be equal to my c.test, and I'm going to pull the estimate out of there. So that's going to be the estimated coefficient. And then my p-value is going to be my c.test $p-value. That's the p-value that I get from doing that correlation test. And here's where we're going to add that conclusion. So if my p-value is less than or equal to 0.05, here's what my conclusion is going to say. The correlation coefficient is whatever my correlation coefficient is, and it is significantly different from 0, and it's going to give me the p-value. However, if my p-value is greater than 0.05, then I want my conclusion statement to say the correlation coefficient is whatever it's equal to, and that it's not significantly different from 0, and give me the associated p-value. Let's look at this on our function with our correlated and uncorrelated data. So notice here, you see that information at the top, right? We've given a conclusion and done a regression analysis all in one function call. We've plotted the regression line, we've listed the correlation coefficient, we've also given the p-value. So much information comes out of this custom function. Now, when you begin a new session in R, your custom functions aren't going to automatically load. But you can customize R itself so that it'll load those functions automatically for you. You do that by creating a .r file called, say, funfunctions.r, and you automatically load it using the following. First, you have to set your working directory, and we use the command setwd. In this case, let's suppose the files were in a file on our desktop called R files. So we would tell R setwd parentheses R files in quotation marks. And so that means that we've now set the working directory to this folder on our desktop. Now, once R looks for the folder of interest, it's going to look for files that can be accessed in R in that directory. So now that it's located there, we can use the source command to bring our functions up. So we would source the file funfunctions.r. And this command accesses and runs all the code that's contained inside. Now, anytime you want to create a scatter plot and automatically include reference lines and regression lines or whatever, you have a custom function that you can add to and build on. And you can make R do so much more for you. I mean, you can even share your work with others. We could download data using commands like read.csv. So that command reads CSV files, or even read.table, data that's separated by a comma or data that's separated by a space. R has so many ways to interact with other sets of data. I mean, much of the data that we use was built in the libraries, but you can bring all sorts of data into the environment. You can even download data from the internet. You could use this command, download.file of the URL that you're interested in. Or the read.csv file. You can actually put a URL into read.csv. And so there are tons more resources like this that are available online. We could even export data from R. And we do that using the write.table command. So this will output our data into a text file. Now you specify the data that'll be maybe comma separated or whatever characters you want. And you do that with the sep command, SEP. Here's how we do that. Write.table of our fun data, the data that we've created, and we're going to write it to this file, fundata.txt. And that data is separated by a comma. Now, once you've done all this work, there are a lot of ways to share it. And the easiest way is to create an R Markdown document. If you're in RStudio, all you do is this. You're going to click on File, and then click on New File, and then select an R Markdown document. Now, it'll ask you for a title and an author, and then it'll ask you to select your default output. Do you want to generate an HTML document, a PDF document, or Microsoft Word? And then RStudio creates the Markdown file for you. And so this allows you to publish to books, to websites, to articles, you name it. R Markdown uses a notebook type interface, and it incorporates your narrative text and your code. So you get these really elegant output that's got code and then graphs and pictures and whatever you want to put in there. You could also use multiple languages, like R interfaces with Python and with SQL. And you can execute code and generate high-quality reports. I hope this course has given you an appreciation for the proper use of statistics and that you leave able to recognize and model all kinds of data. I mean, statistics are all around you. Sometimes they're used well, and sometimes they're not. But you now know how to distinguish between the two. In fact, statistics provides us with an understanding, a way of thinking that enables well-informed decisions. Our statistical brains, they need to be nurtured. And I hope this course has given you new tools and motivation so that statistics comes alive for you.